Hey everyone, this is Euler's method here. So this is really one of the last few things we need to cover. There are a little bit of sprinkling of other BC stuff that we might have to revisit, but this is really the last new thing that you guys need to know. Euler's method, okay? It's not Euler, it's actually Euler. And basically what I want you guys to think of is this. So by now you've gone through both refreshers 5 and 6, right? So slope fields was basically a way to graphically see what your differential equation is. Okay, it was a graphical approach, right? Then for certain differential equations where it is separable, when you have separable differential equations, you were able to solve it analytically, aka algebraically. So that was the analytical approach. Euler's method was something that was left for BC. I honestly do not know why they left it for BC instead of just bringing it on to AB because they're all related. But basically, Euler's method is the numerical approach to getting an idea of what your differential equation looks like. So let me give you an example, okay? So with slope fields, you could kind of follow the slopes to get an idea of what the graph looks like. With separable differential equations, you could actually solve it algebraically to see what the actual equation was. Now, Euler's method was kind of like one of the first approaches before we developed slope fields or separable differential equations, right? Euler's method was a very not efficient, but it gives you an idea of how everything is built in regards to following what Euler was focusing on, which is the slopes at certain coordinates, okay? So Euler's method is just another way of figuring out what the values are of the differential equation, okay? So let me give you an example here. Let's say, suppose that we had a graph, and I'll try to draw this as accurately as possible. Okay, so let's say you had a graph, and I give you two facts. I tell you that y of 0 is 1. Okay, so that's this point right here. And then I'm going to ask you, figure out what y of 4 is. Okay, so here's the issue. We aren't really told what y really is. So like normally I would tell you, y equals x squared plus 4x plus 3. It was explicitly given. But what if that was not given, right? How do we tell where y of 4 is, right? So what they do give us is that they tell us that y prime minus y is equal to 0. So they give us a differential equation. So they give us a differential equation here. We could tell because there's a derivative in it. And notice how it's not explicitly given. Okay? So let's say that we wanted to just kind of pretend that the curve looked a little bit like this. Okay? Obviously, this is not what it is. But let's suppose that this was your particular solution. Right? We'll call that y. Okay, what we're trying to do here is, well, we're trying to figure out, well, at y sub 4, which is basically about right there, what is the y value? Okay, that's what we're trying to figure out. We don't necessarily know what the curve is, and that's the huge issue here. So where do we plug in 4 if we don't have the equation itself, right? So that's where the problem lies. So Euler developed this idea of approximating where we think it'll be, okay? So here's what we can do. We know for a fact that at y of 0, it's 1. So we could actually place a point right here at 1. Okay? And what we're going to do here is this differential equation that we have, it actually tells us about the slope. So I can actually just maneuver this by moving the y to the other side to get y prime is equal to positive y. All I did was I added y to both sides here, in case you didn't see it. Okay, so what this is saying is that the slope will be the same as the y coordinate. That's basically what this equation is saying. And I used a very simple differential equation so it's easier to understand. Okay, not all equations here are going to be this easy to kind of comprehend, but the most important part here is knowing how this works first. Okay, so here's what you do. I know that 0, 1, if I were to plug 1 into y prime, I would get 1. Okay, so this right here is at 0, 1. I know the slope is at 1, so I'm going to draw a little positive slope here. And here's what you guys have to understand. This is the theoretical tangent line that I have here, right? But I'm not going to draw it out completely. I'm actually going to stop. And where we stop is going to be determined by whatever they provide for us here, okay? So let's say we wanted to stop at every integer. So my step size, I'm going to declare that my step size will be 1. So I'm going to stop, use a different color here. I'm going to stop right at 1, right there. Okay, so first off, this point right here is going to be 1. And because the slope is 1, that means I'm rising 1 and I'm running 1. Okay, so that means my new coordinates are going to be 1, 2. Make sure that you understand that before we move on, okay? Okay, so what we're doing now is we're redirecting this so-called ship. Okay, we're redirecting this, or we're updating our slope at this particular point. So now let's take a look at the slope at, and I'll try to color coordinate here. So if we're at 1, 2, that means y prime is equal to 2 based on our differential equation here. Okay, so that means our slope is 2. So that's going to make our tangent line, let me draw this a little bit better, a little bit steeper. But we're going to go ahead and stop at the next stopping point, which is the next integer here, which is at 2. Okay, so at 2, if at the previous point, the peak point 1, 2, if the slope was 2, that means I'm rising up 2 units and running 1 unit to the right. So this should be 2, 4. Okay, and what we're going to do here is we're going to figure out, well, at 2, 4, what is the slope? So in this case, it's going to be 4 based on the equation. So that means my slope at this green point is actually 4, so it's a lot steeper. But I'm going to go ahead and stop at the next point, which is 3. But from the previous green point 2, 4, the slope was 4, meaning I rise 4 and I run 1. So the next coordinates will be 3, 8. Okay, and what I'm going to do here at 3, 8, I'm going to go ahead and find the slope, which would be 8. Okay, so that means my slope is going to be steeper. I rise 8 and I run 1, and I eventually will stop at this 4 here. And that 4 is going to be 4, comma. If I rise 8 units, I'll be at 16. So the approximation here for y of 4 is going to be 16. Okay, so I'll go over how to actually do the problem, but what I want you to notice is we find the slope at a point, and then we have a stoppage at the step size. And at the new point, we redirect our slope. So it's like a ship that's correcting its course, okay? And then we repeat the process. We go to the next step size, and then we redirect with the new slope. And then we go to our next step size, and then we redirect with our new slope. Okay? So some things to note. When we wanted to find out the next point, we had to follow the slope of the previous point. And that's the pattern that you guys are going to use. And I'm going to show you this neat graphical design so that you kind of don't forget about it. So notice how we're just dealing with a bunch of lines here. So it's really just y equals mx plus b. But I'm actually going to write it a little bit differently, okay? I'm actually going to write it as y equals b plus xm. Okay, addition is commutative and multiplication is also commutative. So this is fair game. Okay, here's what we're going to have. B is going to represent the previous y coordinate. I'll just call it y sub 0. Okay, or y naught. Okay, the x is going to represent your step size. And m is going to represent the derivative of the previous point. Okay, so I'll make a note here. This is just previous point. This is also the previous point. This is really what we did in each step. To find out the new y coordinate, we had to take the slope from the previous point and then go from there. All right, so here's what we do. These are the easy multiple choice questions that you have to get. They sometimes get smushed into the FRQs regarding slope fields and separable differential equations. I'll show you that later on as well. But I'm going to show you some problems here, okay? What you're going to do is you're going to start off with your given, whatever the values are, okay? Your next value, you're going to write below it, but towards the left. Notice how I kind of pushed it towards the left here. Okay, and what you do is you plug in your previous plus your step size times the derivative of your previous. And then you keep repeating this. So your last one, usually it's only 2 steps, but sometimes it's more. So let's say that this is your last step. Notice how it's kind of like in a pyramid shape here. It's like a step, like a literal, let me draw it for you, a literal step, okay? So when you do this, you remember that your previous value goes here, plus your step size, times the derivative of your previous. Okay, and I'll show you how that works, all right? Some questions are calculator-based. I should say most questions are calculator-based. Some are not. So you got to get used to using both. Let me get rid of these answers so that you guys... I thought I got rid of these. Whoops. Shame on you, Mr. Lee. Okay, here we go. So these were these 4, 5 questions are AP released questions, okay? So we're going to start off with the first one here. The table above shows values of the derivative, okay, for selected values of x. If f of negative 0.2 is equal to 1, what is the approximation for f of 0.4 using Euler's method with a step size of 0.2 starting at negative 0.2? Okay, there's a lot going on here, but let me paint this out for you, okay? You're first going to start off with what they give you. So we're starting at negative 0.2, so we're going to write f of negative 0.2 is equal to 1. We're going in increments or steps of 0.2. So if you start at negative 0.2, the next one is going to be f of 0. And if you travel another 0.2, the next one will be f of 0.2. And if you go one more, I ran out of space here. Let me scoot this over. And you want to keep traveling until you get to where you want. They're asking for f of 0.4 here. So notice how it's staggered like a step. Okay? So here we go. It takes some getting used to, but you guys will see it right away. F of 0 will be the previous value. So f of negative 0.2 is 1. Okay? Plus your step size. Your step size never changes. It's positive 0.2 right here. So it'll be 0.2 times the derivative of the previous value. So in here, you want the derivative of the previous value. Okay? If you take a look at that, it's 0.8. So I'm going to put in 0.8 here. All right. Now this is number 77, so I can assume that it's a calculator question. 1 plus 0.2 times 0.8, I believe that's 1.16. Okay. All right, let's keep going. Here we go. So to go to f of 0.2, we plug in our previous value. F of 0 is 1.16 plus the step size times the derivative of the previous coordinate. So we're finding f prime of 0, which is 1.2. Okay, everything is based off of its previous coordinate, okay? This right here comes out to, oh gosh, 0.2, 1.2 times 0.2 is 0.24 plus 1.16. What is that, 1.40? I should really use a calculator. I think that's good. Okay, so the last one. We use the previous value, so f of 0.2 is really 1.40 plus the same step size times the derivative of the previous x coordinate. So the derivative at 0.2 is 1.7, which equals, I'm actually going to type this out, 0.2 times 1.7 plus 1.4. So we get 1.74, which is what we're looking for. Okay? So again, previous y value, previous derivative, previous y value, previous derivative. Did you guys hear my son chuckle right now? Oh my gosh. Okay. Previous y value, previous y value's derivative. But notice what's always constant is the step size. All right. Okay, so this one here was a table, right? Nothing changes if you don't have a table. Okay, you might have to do a little bit of work, but I'm going to have you guys jump to number 83 right now, since there's a table there. Try it out. Press play whenever you're ready. Okay, so first thing you want to do is find out where you're starting. So the starting is the given here. So f of 1 is 4. So we're going to start off with f of 1 is equal to 4. And we're trying to get to f of 2, but with increments of 0.5. So the next one is going to be f of 1.5 and then f of 2. Okay, so we only have to take 2 steps here. The last one we had to take 3, I think. Okay, so here we go. F of 1.5 will be the previous y value plus the step size times the derivative of the previous coordinate, which is 0.2. Okay, so if you multiply that out, add the 4, you should get 4.1. Okay. And to get the last one, f of 2, it's the previous value, which is 4.1, plus the same step size times the derivative of the previous coordinate. So add 1.5, it's 0.5. Plus 4.1. Okay, so here you should get 4.35. It's a lot of computation, but these should be your easy points. There you go. Okay, if you got that, great. If you didn't and you're not sure why, text me right away, okay? Okay, so let's take a look at number 10 now. Notice how number 10 is in the lower values, so you could kind of assume that that's not a calculator active question there, okay? They give you an equation instead, so you have to produce your own values. But here we go. I'll go ahead and do it over here. So we start off with what we know. F of 2 equals 8. Okay, we're trying to get to f of 3 with 2 equal steps. So to get to 2 equal steps, we're going to have to travel by 0.5. So sometimes they don't tell you literally what the step size is, but you guys are smart enough to figure that out, okay? All right, here we go. So f of 2.5 is going to be the previous y coordinate, which is 8, plus the step size, which is 0.5, times the derivative of the previous coordinate. So notice how this is the derivative right here, but the derivative is determined by x minus y. So if I did x minus y of the previous coordinate, I'll get -6. Okay, let me scoot this over because I think I need more space. I'll do it over, stop it. Right there, that should be enough space. Equals, so this should come out to what, 0.5, half of -6 is -3, plus the 8 is 5. Remember that this is not a calculator active question, so try not to use it, okay? So f of 3 will be the previous y value, 5, plus the same step size, times the derivative of the previous point. Let me highlight it for you, okay? The previous point is 2.5, comma 5. So that'll be 2.5 minus 5, which is -2.5. That gives me 5 minus, oh gosh, 25 times 5 is 125, right? So that's 1.25. And if I subtract that, I get 3.75, which looks like, what was that, 3 3/4? So that's 15/4. There you go, okay? Now, some of you might have started with fractions. You would have ended up with fractions. Personally, I like to just, especially if it's a quarter or a half, I deal with decimals and then I'll figure it out later. But notice how it's really the same thing. Previous y coordinate plus the step size times the previous derivative. Okay, go ahead and try number 9 here. Press play when you're ready. Okay, This one is super tricky, but very easy to do. Oh, my son is awesome. Okay, you start off with what you give, or what you're given, f of 1 equals 2, and you try to go 2 steps to get to f of 0. So this one here would definitely be 0.5. Now, what I do want to stress is, what is the step size? And this is where it throws some people off. The step size here, and you guys want to write this down, is that it goes down 0.5 units. You started off at 1 and you're going backwards to 0. So your step size is actually a negative value, okay? All right, here we go. So f of 0.5 is the previous unit plus the step size, negative 0.5, times the derivative of the previous point. So that's going to be 2 times 2 minus the 1, which is 3. And what does that come out to? Negative 1.5, 0.5. That comes out to 0.5. I don't have enough space here. Okay, f of 0 will be the previous unit, 0.5, plus the step size of negative 0.5 times the derivative of the previous point. So 0.5 comma 0.5. So 2 times 0.5 minus 0.5. That should come out to 0.5. Half of 2 is 1. 1 minus a half is a half. So this is 0.5 minus 0.25, which gives us a quarter left, which is C. If you don't like decimals, stick with fractions. This is just a matter of a preference, okay? All right, there's one more. Go ahead and try this one. Press play when you're ready. Okay, you start off with what you're given. F of 1 is equal to 0. You know you want f of 2. They want 2 steps of equal length, so this missing one should be f of 1.5. Looks like the step size is 0.5, positive, okay? So here, you start off with your previous y coordinate plus the step size, which is 0.5, times the derivative of the previous coordinate, so that's 2 times 1 plus 0, that comes out to 2. Okay, half of 2 is going to be 1. Right, f of 2 is the previous y coordinate plus the same step size times the derivative of the previous point. So that's going to be 2 times 1.5 plus 1. 2 times 1.5 is 3 plus the 1 is a 4. Okay, half of 4 is 2 plus the 1 is 3. There you have it. A little bit of work to be done, but I want you guys to understand that it's easy work. Just a lot of computations, okay? But do use the staggering staircase so that you remember how it kind of works there. Everything builds off of the previous step. To get to one step, you have to start from the previous step, right? Kind of makes sense. Anyways, try this out. Let me know how it goes, and we'll go from there.